All right, welcome everyone, and thank you for joining us for our third Zoom STEM mentoring session with Ashini Modi. Today, we are going to be talking about chemistry 101, helping you guys to work on your science fair projects and all that entails. So, without further ado, I will turn it over to Ashini.
Awesome, thank you so much. Okay. So before we get started, if everyone can just get out a piece of paper really quickly, because we're going to be doing a little bit of hands-on chemistry. So I'll give you just a second to get out a piece of paper and a pencil, and then we're going to get started. Okay, so our topic today is, like Ms. Bonnet said, chemistry. We're going to be learning about elements, chemicals, reactions, and more, and then we're going to learn about how they apply to everyday life. So we're going to have an introduction to chemistry. We're going to talk about the 5 different branches of chemistry. Then we're going to do some chemistry ourselves and its application to the real world. So chemistry involves the composition of matter and the changes that these matter undergo. And it's the science that deals with the materials found in our universe and the changes that these materials undergo here on Earth and also in our universe and in our bodies as well. So one thing that we do every single day that involves so much chemistry is cooking. So cooking explains how ingredients interact as you mix them, how food changes as you heat it, and even how it rots. So when you heat up food, that's chemistry that's occurring. When food goes bad, that's also chemistry that's occurring. When you're cleaning, chemistry can explain how soap gets rid of grease and cleans dishes, or your hands. So every single thing that is involved in the making of soaps and is involved in the cleaning of things around your house involves chemistry. Medicine. So chemistry can explain how vitamins keep us healthy when we eat them and how medications work when we get sick. And there are scientists every day currently working on developing a vaccine to keep us safe from the coronavirus, and that involves chemistry. Also environmental issues. So chemistry might explain why oil spills are really bad for the oceans and how we can clean up pollution in the air. So a couple of years back when we had the oil spill in the Gulf, it was chemicals that were used to clean up this oil spill. And it was also chemicals that were put in the oil that led to our oceans being messed up. So chemistry really explains a lot of these concepts, and it can help solve a lot of concepts as well. So one of the main things that we need to learn before we start going deep into chemistry is what is matter. Matter is anything that has mass and occupies space, which is volume. So what is mass? Mass is basically how much something weighs, and mass can obviously change depending on how much gravity you have. But matter it can be invisible or it can be visible, but it's anything that's around us that has this mass and has a volume as well. So what's the difference between mass and weight? So there are 3 different types of states of matter. They have solid, liquid, and gas. Mass measures the amount of matter that an object contains. So example of that would be grams. But weight is the force with which Earth pulls on an object, which would be newtons. So for example, if we were standing on the moon, we would have the same mass, but we would have a different weight because the gravity is pulling with less of a force. So you have 5 branches of chemistry. You have inorganic, organic, analytical, physical, and biochemistry. So inorganic is a study of chemicals that do not contain carbon. So carbon is a very, very important element that we will talk about a little bit more later. You have organic chemistry, which is a study of chemicals that do contain carbon, and it originated in living organisms. You have analytical chemistry, which is a study of the composition of matter. Physical chemistry, which we will go into detail today, which is the study of the mechanism, rate, and energy transfer that happens when matter undergoes change. So matter is constantly undergoing change. It can happen in our bodies, it can happen in the environment as well. And you also have biochemistry, which is a study of chemical pathways and breakdown of fuels in living organisms. So all of the chemistry that happens in our bodies is due to biochemistry, and biochemistry is the study of those chemical reactions. So let's do a little bit of an overview. What is inorganic chemistry? So like I said earlier, it's the study of non-carbon containing compounds. So there are around 100,000 known inorganic compounds. You have acids, bases, salts, oxides, which contain oxygen. An example of an inorganic compound would be NaCl, which is actually salt that's on the table. You also have silicon oxide, which is used in computer chips and also solar panels. You have sapphire, which is a gemstone, and you have sulfuric acid, which is found in fertilizers. So inorganic chemistry is readily available all around us. You also have organic chemistry, which is the study of chemistry that contains carbon. Carbon is present in all forms of life. It is the fourth most abundant element in our universe, and there are 2 million known organic compounds. So, can anyone tell me what they think the number one most abundant element in our universe is? Anyone? It's actually the most common one, the first one that you would think of, and it's hydrogen. Hydrogen is the most abundant element in our universe, and carbon is the fourth most. You also have analytical chemistry, which is the study of composition of matter and how much exists. An example would be mass spectrophotometer and gas chromatography. And so analytical chemistry is just study of matter that exists all around us. You also have physical chemistry, which is the study of what happens when matter undergoes change. So, matter is constantly undergoing change all around us. When something melts, the matter is undergoing change. It's going from solid to liquid. When you're boiling water, it goes from liquid to gas. So, matter is constantly changing all around us. It also incorporates the ideas of physics, such as energy. So when you're heating water, you're putting energy into that water, and that's why it's able to go to a gaseous stage. So that's what physical chemistry entails. And then finally, you have biochemistry, which is a study of chemical processes in living organisms such as plants, animals, and humans. And it looks at the chemistry of the cell and the different organelles. So if you were in our past session, you know what organelles are. And something really interesting that biochemists study is they study DNA. And we'll talk a little bit more about DNA later. So, a little bit of the history about the field of chemistry. So, here are some very famous historians. You have Alfred Nobel, who invented the dynamite, which is used today to build roads, railroads, and tunnels. And the Nobel Prize was actually named after him. You have Lavoisier, who is the father of chemistry. He discovered the law of conservation of mass, which is that mass cannot be created nor destroyed, which is a very important concept in chemistry. He also explained burning as a reaction that happens with oxygen. So whenever you have a fire that you're building, the one thing that's really causing that fire to burn is oxygen, and that happens in what's known as a combustion reaction. You also have another really important chemist. His name was Mendeleev, and he invented the periodic table, which we will look at later. You have Marie Curie. She discovered radioactivity, and she helped find the concept of X-ray imaging. So whenever you go to the doctor, if you have a broken bone, and how you're able to see your bone, that's because of Marie Curie, who developed the concept of the X-ray. You have Frederick Sanger, who founded the chemical method to sequence DNA. He was a famous biochemist. And you have Mario Molina, who studied the Antarctic ozone layer and explained the threat that chlorofluorocarbon gases have on the destruction of our ozone layer. So today what we're seeing is that our environment is getting really hot, and that's causing global warming. So Mario Molina is one person who's helping to explain the threat that some gases on Earth are having in the destruction of our ozone layer. So, something really important that's a big part of matter are elements. Elements are substances that cannot be broken down into smaller parts. So, if you try to cut an element in half, you're never ever going to be able to split that element into a smaller part that's not the element. So, can anyone name some elements? We talked about hydrogen, we talked about carbon. Does anyone know any other elements? Let's see, I'm gonna have to start calling on people. Shabad, do you know any elements?
Well, Wesley raised his hand.
Oh, he did. Okay.
Yes.
Okay.
Wesley,
Nitrogen and phosphorus.
Yeah, nitrogen and phosphorus, those are two very, very important elements. Shubha, did you say something?
Um, um, I would say water as an element, but that's just hydrogen, isn't it?
Yeah, so water is not an element, but we'll talk about that later. Water is actually known as something called a compound, but it is made of elements and it's made of hydrogen and oxygen. So that was a really good observation.
Okay, thank you.
So the way elements are organized are known as the periodic table of elements. And you can see an example of a periodic table here. So like I said earlier, in 1864, Dmitry Mendeleev created this periodic table as a way to organize elements by their atomic size and their atomic number. So on the left-hand side of the periodic table are metals. So metals are, as you can see around us, they're shiny, they're malleable, and they're really good conductors of heat and energy. And on the right-hand side, generally you have nonmetals, which are gaseous, really dull, and they're very poor conductors. So Mendeleev found a way to organize these elements by their atomic number. So we're going to go a little bit more into detail about what an atomic number is next. So this is, if you zoom into one of the elements on in the periodic table, you'll see something that looks like this. So the element symbol is what's in the center. So for example, the element symbol of oxygen is just an O, and its atomic number is 8. So what atomic number means is that's the number of protons in the atom that the element contains. So protons exist in the center of an atom and they're in the nucleus of the atom. So you have protons, they're also the number of electrons. You also have the atomic weight, which is the number of protons plus neutrons. So atoms. Atoms, all elements are made up of only one type of atom. So if you have phosphorus, phosphorus is only made up of phosphorus atoms. If you have hydrogen, it's only made up of hydrogen atoms. And it's indivisible by normal chemical means. So you really can't split an atom into anything else. Yes, it's made of protons, neutrons, and electrons, but you can't really split it up. So within an atom, though, you have subatomic particles. You have protons. Protons are positively charged. And like I said, they're located in the nucleus of the atom. So the nucleus is what's in the center of an atom. And atomic number is the number of protons. So the number that you saw at the very top of that element, that's the atomic number, and that codes for the number of positively charged subatomic particles known as the proton inside the atom. You also have neutrons, which are neutrally charged. They don't really have any charge. In the nucleus, neutrons are located with the protons, and protons plus neutrons make the mass of the atom. So as you can see here in the center are the protons, and you also have the neutrons. And around that, you have what are known as electrons. And electrons are negatively charged. They're located outside the nucleus in shells that orbit the center, and they don't really have a mass, so they don't factor into the overall mass. So in an atom that's balanced, the number of protons actually equals the number of electrons. So what does that mean for the charge of the entire atom? Raise your hand if you know the answer. If you have an equal number of positive charges and an equal number of negative charges, what does that mean for the overall charge of the atom? They cancel each other out, right? So if you have an equal number of positive, equal number of negative, that's zero. It doesn't have a charge anymore. So in a balanced atom, it actually doesn't have any charge. So we're going to identify some numbers now by looking at these elements. So on the left-hand side is helium. How many electrons does helium have by looking at the element here? Shabit?
4.0026 electrons.
No, that's a
Oh
really
wait, no, two.
It's two, yes, awesome. So the number at the very top The number 2 codes for the number of protons and the number of electrons. So there are 2 electrons in helium. But the number 4.0026, which you can kind of round to 4 here, is going to be the mass of the element. So that's the number of protons plus the number of neutrons. For tellurium, how many protons does it have? Let's see, Wesley?
52.
52, that's correct. It has 52 protons. And here is a little bit more difficult one. How many neutrons does argon have? So the way you find neutrons is actually by subtracting the atomic mass and the number of protons. So the atomic mass here is around 40, and the number of protons is 18. So 40 minus 18 is
32.
almost.
And Wesley has
Wait.
his hand up.
Oh, Wesley has his hand up. Wesley, how many neutrons does argon have?
22.
22 neutrons, that's correct. So now you guys know how to identify elements in a periodic table, which is so cool. You know exactly what these atoms look like because you know how many protons they have, you know how many neutrons they have, and you know how many electrons they have. So now we're going to do something just a little bit more difficult. So like I told you guys to get out your papers in the beginning of the session, now's the time to get that paper out and your pencil because we're going to be drawing some diagrams of atoms. So every atom has multiple energy levels. So what an energy level means is those are the shells that the electrons hang out in. So we represent every energy level with a circle around the nucleus, and every dot on the energy level is going to be an electron. So the first energy level can only hold 2 electrons to be happy. The second energy level can only hold 8 electrons, and the third can only hold 18. So if the energy levels are full, meaning they have these numbers, that means they're really happy and they don't want to bond with anything else. And so, but an energy level cannot have more than these numbers. So the first can only have a max of 2, and the second can have only a max of 8. So as you can see here, here's the Bohr diagram of oxygen. So in the beginning of drawing a Bohr diagram, you have to draw the symbol of the element in the center. So the symbol of oxygen is O. And we know that oxygen has 8 electrons because we know that from looking at its periodic table and seeing that the number 8 is its atomic number. So you're going to draw those electrons around the center. So in the first orbital, you're going to have 2 electrons, 1, 2, because it can only hold 2. And then you're going to draw another circle. And the second circle is going to have 6 electrons because 1, 2, 3, 4, 5, 6. And you're not going to add any more because it only has 8 electrons. So now let's draw the orbital diagram of neon. So here's neon. From looking at neon, you can tell that it has 10 electrons and it also has 10 protons. So let's see if you guys can draw the Bohr diagram of neon. I'm going to give you guys around 2 minutes to draw it. So remember, in the center, you're going to have the symbol of neon. And you're going to draw as many energy levels as you need by drawing circles, and then you're going to draw the number of electrons on each energy level. And remember, the first one can only hold 2 electrons, and the second one can only hold 8. And just give me a thumbs up when you guys think that you're done drawing your orbital diagram. All right, so I think you guys should be about done right now. If you're not, that's okay. We're going to go ahead and check it though. So did you guys get something that looks like this? Give me a thumbs up if you did.
Yeah, I got something around that.
Yeah. Awesome. So in the center, you have the symbol of neon. And then because we saw that the atomic number of neon was 10, you're going to have 10 electrons. So in the first one, you're going to have 2 dots, and in the second one, you're going to have 8. So something interesting that you may notice about neon is that in its second energy level, it's completely full. It has all 8 electrons there. So it's actually called a noble gas. It's noble because it's so happy because its valence shell is full. So that means it doesn't want to bond with anyone, and it is a completely stable atom. So molecules occur when 2 or more atoms combine chemically together. When 2 nitrogen atoms combine, it makes a nitrogen molecule, and a nitrogen molecule is actually called nitrogen gas. So if you have nitrogen gas in our atmosphere, those are 2 nitrogen atoms stuck together, creating a nitrogen molecule. And you can see how that works here. You see you have 2 nitrogen atoms, and then they bond together and they create this nitrogen molecule. Compounds occur when 2 or more different atoms bond together. For example, you have 2 hydrogen atoms plus 1 oxygen atom, and that makes water. So water, like Shebad was talking about in the beginning, water is actually the combination of 2 hydrogen atoms and 1 oxygen atom, and they bond together, as you can see in this picture at the bottom, and it creates H2O. And there are about 600 billion trillion water molecules in 1 tablespoon of water. So it just gives you an idea of how small water molecules are and how many, exactly, Shabbat, that's so many water molecules. So just imagine how many hydrogen atoms there are in 1 tablespoon of water. That is a lot. So they're extremely small, so that's why you can't really separate them. Chemical reactions, like we just talked about before, so 2H plus O equals H2O, that's a chemical reaction. So they occur when 2 or more atoms, molecules, or compounds combine with or dissociate with each other. And chemical reactions happen all around us all the time. Like I said before, chemical reactions happen when you're cooking. If something is metal and it gets exposed to oxygen and water, it might rust, and that's a chemical reaction. So if you ever see rust on your bike, that's a chemical reaction. If a candle is burning, as you can see here, that's a combustion reaction, and that's happening because of water, because of oxygen. If you have anaerobic respiration, breathing, that's a chemical reaction. Digestion, that's a chemical reaction happening in your stomach. Photosynthesis, so that's the process of how plants get their food. That's a chemical reaction. So everything around us is constantly having a chemical reaction, which is just so cool to think about. Another really important concept of chemistry is the concept of acids and bases. So all around us, in our kitchen maybe, we have so many different acids and bases. So lemon, that's an acid. Vinegar, that's an acid. Tomato, that's also acidic. Water is actually neutral, which means it doesn't have it has a pH of 7, and it's not acidic or basic. Baking soda is basic, and soap is actually a basic solution. So acids have a really low pH of around 1 to 6, and they taste really sour. So you think of lemons, that's acidic because it tastes sour. Bases have a really high pH, and that's pH is the concentration of hydrogen in that. So they have a really high pH, and it has a pH of around 8 to 14, and they taste really bitter. So I hope no one's tasted soap, but it would taste really bitter if you've tasted that. So acids and bases actually neutralize each other. And so that's why when you taste water, it doesn't really have a taste because it's neither acidic, it doesn't taste sour, and it doesn't taste bitter. It's right in the center. So a fun fact is that our stomachs use acid to break down the food that we eat. And batteries use a really strong acid and metal plates to help create electricity. There's tons of acids and tons of bases all around us, and you can identify that. Oh, something else really cool is that milk is actually acidic. So who would have thought that milk would be slightly acidic? So in every chemical reaction, you have lots of energy that's involved. And the only way reactions can happen around us is if there's energy. Chemical energy is the energy that's stored in bonds between atoms. And when bonds are broken, energy is released. So if you have HO being broken down into 2H plus O, energy is being released in that process. You can have electrical energy, which is the movement of charged particles. In your house, electrical energy is flowing through the wires. So if you turn on the light, that's electrical energy. Mechanical energy is energy directly involved in moving matter. So if you move your arms, if you're pushing something, that's mechanical energy. And you also have radiant energy, which is energy that travels in the form of waves. So who would have thought that energy might travel in forms of waves? I mean, like you can go to the beach and you see waves on the ocean, but they're actually waves that are invisible to us. And they're very small and they're all around us. So some examples of waves are X-rays and radio waves, and also visible light. Visible light is waves as well. And we can tell the different types of waves by looking at an electromagnetic spectrum. So on the left-hand side are waves with a very, very short wavelength, and they're really high energy. So you think of X-rays. X-rays are really, really high energy. Visible light is in the middle. So everything that we can see around us with our eyes, that has a wavelength that's kind of short and kind of long. It's in the middle. Microwave energy is actually really long. It doesn't have very high energy. And radio waves are one of the longest wavelengths, meaning they have very, very low energy. So there are so many different types of energy all around us that are causing reactions to happen and that are also traveling in the forms of waves so that we can see things and study things. So everything that we talked about before was physical chemistry and analytical chemistry. So this was the kind of chemistry that you might conduct in a chemistry lab by pouring substances together or seeing if ice is melting. That's physical and analytical chemistry. But you also have something called biochemistry, which is the study of chemical interactions in living things. Biochemists study the structure of biomolecules, and some of the most common elements found in living organisms are carbon, oxygen, nitrogen, hydrogen, phosphorus, and sulfur. Something that biochemists like to study is DNA and the processes that are involved in the formation of DNA and the way DNA can be used to help cure things. So DNA is a material that carries all of the information about how a living thing will look and how it will function. It is in every cell of every living thing, and it's found in the nucleus of the cell. So if you were at our past session, you know what the nucleus of the cell is. It's the center point of the cell, basically, and DNA is found in that. So DNA has multiple parts. One of the main parts of DNA is nucleotides. Nucleotides are the building blocks of nucleic acids. So nucleic acids, the DNA stands for deoxyribose nucleic acid. So nucleic acid are a broad form of all different types of DNA. You have phosphate molecules, which comes from the name phosphorus. You have nitrogenous bases, which attach to the sugars, the 5-carbon sugars. And you can see the 5-carbon sugar here, and you can kind of think of the 5-carbon sugar in DNA as a glue that holds the phosphate group and the nitrogenous bases together. So these are very, very small. You think of DNA, you can barely see DNA. But these are a subclass of what's included inside DNA. So it contains a phosphorus, it contains sugar, and it also contains a nitrogenous base. So biochemistry and physical chemistry and analytical chemistry, these are all things that scientists all around us study. If you're interested in chemistry, there's so many jobs out there that you might feel like you want to conduct in the future. So you can be a patent attorney. These are people that make patents on different chemicals and on different substances. You could be a pharmacist, meaning that you're distributing medications to people. And medications involve lots of chemistry in making them. You can be a forensic chemist, meaning that you can study fingerprints and you can study DNA left at crime scenes. You can be a biochemist and biotechnologist who are making medicines and therapies and technologies for us to help us with medicine. You can also be an agricultural chemist, which is someone that creates pesticides and make sure that pesticides are safe for consuming as well. You could be a food and flavor chemist, which is testing the flavors of foods, making sure that food is safe, and you would work for the Food and Drug Administration possibly. And you can also be a cosmetic chemist, someone that makes makeup products and skincare products. And so as you can see, there's lots of different branches of chemistry that one can go into if you're interested in it, and lots of different career choices and paths as well. So thinking about that, you can try to be a chemist yourself, even if you don't have a degree. So here is a really cool short project that you can do. If you're interested in it, you can just take a screenshot of this slide right now, but it's called chromatography. And chromatography is a laboratory technique for separation of a mixture through its affinity. So chromatography is super interesting because it's used in making vaccines, such as the COVID vaccine that's being made right now. It's used in food testing, it's used in forensic testing, and so much more. And it's also used in labs to purify blood samples and even vaccines in their development, like I said before. So here are the materials that you'll need to use if you want to conduct your own chromatography experiment and be a chemist. And here are the instructions on the link provided. So you can just, I'll send this link in the chat after the program. And you can just take a screenshot of this slide and then you can conduct it when you're at home. So now we're going to hear from our guest speaker, Dr. Gulshan Soonawala. She is an associate professor of biochemistry and molecular biology at LSU Health, and she's doing some really interesting research right now. So she's going to talk to you about how she got interested in her field and some really important research that she's doing currently. So let's welcome Dr. Soonawala.
Hi, guys. I had a good refresher course in chemistry today. Thanks, Ashini, for inviting me. Can you hear me? Can you all hear me, guys?
Yes, we can hear you.
Okay. So I'd like to share with you my story and how I got into research. And in doing so, I'd like to share with you my screen and a little bit about, okay. Okay, can you all see my screen, guys?
Yes.
Okay, so I started out as a dentist and then specialized in oral medicine and oral surgery. But I always realized that there are so many diseases we do not know much about, and we do not have many cures. So the only way I thought I could make a difference is to do some more research into what causes diseases and how we can help people. So that is how I went into research. And here I want to give you a flavor of how research can make a difference. And so I work in the Department of Biochemistry and Molecular Biology at LSU Health Sciences Center, where we work, some people work on human cells, others work on yeasts, trying to find out answers to different questions that they pose. There are others who work on how molecules interact. As Ashini said, that biochemistry is nothing but how molecules in the cells are interacting with the DNA, with the messenger RNA, with the proteins. How are things going around in the cell to keep it functioning? So people are devoting their energies towards finding how this interaction occurs. And there are some who are also working on viruses. And I will segue into what is now going on is the pandemic COVID-19. This is not the topic I'm working on, but I thought I'd give you a brief understanding of where we are in this pandemic and what causes it and how they have come about developing the vaccine. So the COVID-19 pandemic stands for coronavirus infectious disease 19 because in 2019 in Wuhan, China, that is when this virus crossed into the human species and started to cause disease. This virus is called the SARS-CoV-2 virus because SARS stands for Severe Acute Respiratory Syndrome Coronavirus 2, and it is responsible for causing the COVID-19. As you all are well aware, COVID-19 has resulted in a lot of deaths around our country as well as worldwide. Here you can see that almost every nation on earth or every continent has COVID-19, and death rates have spiked. Say from beginning of January 2020 to now December, you can see the trend as to the number of death rates in the lower panel out here. So as of now, we have no treatments to cure COVID-19. The only thing we can do is to prevent it. And to prevent it, we are developing vaccines. So vaccines have been used for over 200 years. Now, if you go back, you'd remember Edward Jenner. He was the one who pioneered the smallpox vaccine. Then that was at the end of the 19th century, around 1896, if I mistake not. And then came Jonas Salk in the 20th century, where he came along with polio vaccine. And because of these pioneering discoveries, we do not see these diseases in our population now. We have eradicated smallpox, polio. So the same idea was that we can eradicate COVID-19. So previously we had used either dead, inactive, or non-disease causing viruses for vaccines. But for COVID-19 vaccine, they used a revolutionary approach, a different approach. And these are the pioneers. To the left of the screen, you'll see the pioneers from Pfizer, from BioNTech, as well as from Moderna, who developed the new COVID-19 vaccine. So the virus has outer protein. You can see them as knobs out here. If you can see my cursor. Can you all see my cursor out here, guys?
Yes.
Okay, so you can see these knobs. They are the spike proteins. This is the protein by which the virus attaches to the human cell. Once attaches to the human cell, it can easily get into the human cell and infect human cells. So the virus, this is the outer coat of the virus. Inside the genetic material of the virus is a single-stranded messenger RNA. Ashini talked about DNA in human cells, our human cells. That is our genetic code. Virus uses mRNA as the genetic code to encode for its proteins. So the COVID-19 vaccine was developed using not the entire virus mRNA, but just a part of the virus mRNA that encodes the spike protein. So what they did was they used the spike mRNA and injected it into humans so that the human cells could make the spike protein. Not the entire virus, just a part of that protein that the virus encodes. Okay? So the idea behind it is that our body defense mechanisms will see that protein as foreign and develop antibodies to it. Just the same way virus influenza or the flu virus, how our body fights it, same way it uses the same defense mechanisms, the antibodies that are generated to fight this virus. Everybody with me, guys? Or am I going too fast? Okay,
Perfect.
good. So in short, what we are doing by the vaccine is trying to make our bodies develop those antibodies to fight the virus. So when a vaccinated person comes in contact with the virus, the antibodies that are already generated in that person will bind the virus preventing it from interacting with human cells, therefore preventing disease. This is how this COVID-19 vaccine has been developed. And I think it has been revolutionary in the sense that in a very short period of time, from the time we started seeing an increase in death rates in March to December, you're looking at 9 months. We have a vaccine. We had never done that before. Before, vaccines used to take 3 to 5 years to be made. We have done it in 9 months, and that is commendable. And so I'll leave you with this idea that research can affect many aspects of medicine. And I want to give you the flavor that investing yourself in research could benefit the community or the world. And that's all I'll tell today. I hope you have enjoyed it. If you have any questions, shoot me a chat message or ask me a question.
That's awesome. Thank you so much. I loved learning about how exactly the COVID vaccine was developed and all the mechanisms of that. And I think that's really important for us to learn now because it's extremely relevant today. And he was extremely right that research plays an extremely important role in our lives, and we should invest ourselves into that. And I know that because you guys are all here on a Saturday, you are invested in science and research. So I hope that you decide to pursue that. So now we're going to play a fun game called Kahoot. So I'm going to share my screen with the Kahoot link really quickly, and we're going to get started. Okay. Sorry, it's taking a little while to load. Okay. Here we go. Pin, you just go to kahoot.it and then you type in the game pin and then you type in your name. The first question is, what is matter? With a shape that doesn't has a mass and takes up space, or anything that you can see. Yes, anything that has mass and takes up space. What is organic chemistry? The study of molecules that don't have carbon, the study of chemicals that contain carbon, the study of chemicals that contain oxygen, or the study of chemicals and molecules in living things? It is the study of chemicals that contain carbon. Who invented the periodic table? Was it Mendeleev? Was it Mendel, Nobel, or Curie? Mendeleev, Mendel. Yes, that's correct. It was Mendeleev. He invented the periodic table. Mendel was actually the person who identified the way that traits pass on to offspring. Nobel is the person who the Nobel Prize is named after. And Marie Curie was the person who discovered the concept of the X-ray. How many neutrons does phosphorus have? So as you can see here, it has the number 15 at the top, which is the atomic number, and its atomic mass is 31. So how many neutrons does it have? And, oh no, no one got this one right. Okay, so how do we find the number of neutrons? So you take the atomic mass, which in this case was 31, and you subtract the atomic number, which was 15. So the atomic number, like I said, is the number of protons, and the atomic mass is protons plus neutrons. So 31 minus 15 is 16. And one more question. True or false? Perfecta whitening toothpaste has a pH of 4.67. It is a basic solution. Is this true or is this false? And the answer was false. So when something has a pH of 4.67, like I said, 7 is our neutral number. So water has a pH of 7, and anything less than 7, so in that range of 1 to 6 means that's acidic, and anything in the range of 8 onwards is going to be basic. So toothpaste is actually an acidic solution, and that's how it's able to clean our teeth. But on the contrary, soap is a basic solution. So that's something that's really interesting to think about. So our leaderboard is number 1 is Leslie Lynn. That's awesome. So I hope you guys learned a little bit about chemistry today. And I hope you maybe like chemistry, maybe you want to go into one of the jobs in chemistry that I described earlier. But that's okay if you didn't do 100% great today. Chemistry is really hard. It's a lot of conceptual things. You really can't visualize a lot of it. So it takes a little bit of a hang to get perfect at it, but that's okay. You guys learned some really hard concepts today, and you're super young, so that's awesome, and you're going to be prepared for high school chemistry, and you might even go into chemistry as a career. So I'm going to share my screen one more time with that experiment that I was talking to you guys about, so you can go ahead and look it up, and I think it's already in the chat, but I'm going to share my screen with it one more time. And I just want to thank Dr. Gulshan so much for coming on today and speaking and giving us an overview about the coronavirus vaccine and why research is so important. And I think it was really impactful. So I just want to say thank you for that. And I hope you guys enjoyed this session. I'm going to share my screen really quickly and then.
You're most welcome, Ashini.
And while Ashini is getting her screen ready, I just want to thank all of you again for joining us for the STEM mentoring session. Thank you, Dr. Golshan, for helping us out today. And thank you, Ashini, for putting these great programs together. And if any of you would like to see any of our former sessions that we've had, or if there was something in this one you want to watch again, please check it out on the Shreve Memorial Library YouTube channel. This video will be uploaded after the conclusion of our event today. So again, thank you everyone for joining us.
And here is the chromatography experiment. Let me go ahead and post the link in the chat one more time in case you didn't get it the first time. So make sure you get that link saved. I'm going to send out another Google form to all of you guys later. And then you can go ahead and fill that Google form out about how you like the session, what you would like to hear next. And there are also going to be some information about an upcoming science fair that we're going to get coordinated. So thank you guys so much for coming. Once again, I really appreciate Dr. Gulshan for coming and speaking today. And I hope to see all of you guys again soon.
Bye-bye, guys. Take care.